Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
I want you to just stop for a second. Whatever you're doing, put down the phone, just listen. If it's quiet enough, maybe you can hear a clock. Or, I don't know, the hum of your computer. But even if it's dead silent, you feel it, don't you?
Oh, absolutely. That constant forward motion.
Yeah, that relentless push. A second passes, then another. You can remember the coffee you had this morning, right? The taste, the warmth. But you can't remember the dinner you're going to have tonight.
It's maybe the most fundamental part of being human. We're born, we age.
It's a one-way street.
It feels like the bedrock of reality. Like if you took everything else, so all the matter, all the energy, gravity, everything, you still feel like time would be there just ticking away in the dark.
Waiting for something to happen.
Yeah. But,
Yeah.
and this is the idea that has been just completely messing with my head for the past few days. What if that feeling is an illusion?
Illusion is a strong word. Maybe a secondary effect. A byproduct of something much, much deeper. We've been going through some really fascinating, really dense material about what some are calling a quiet revolution in physics. And the headline claim is just staggering. Time is not fundamental.
Right. It's not the foundation. The proposal is that time is actually emerging from something else entirely.
And that something else is information.
Something we usually think of as abstract, bits and bytes. But physicists are starting to treat it as a real physical thing.
The argument here, if I'm getting it right, is that the universe is basically a giant recording device.
In a manner of speaking, yes. And what we call time is just the act of that device, recording, writing things into its own memory.
Okay, we've got to unpack this very carefully. Because time is memory sounds like poetry.
It does, but the physics behind it is pretty serious.
I want to start with the problem itself. Because I think most of us, myself included, kind of assume science has time figured out. We've got atomic clocks, GPS. We're pretty good at knowing what time it is.
We know how to measure it. That's a very different thing from knowing what it is. And honestly, for over a century, physics has been, embarrassed by time.
Embarrassed, that's not a word I associate with physics.
It's the only word that really fits. Because, you see, we have two grand theories of the universe, two main rule books. On one side, you've got Albert Einstein, general relativity.
The big stuff. Planets, stars, galaxies, gravity, the cosmic scale.
Exactly. And in Einstein's world, time is not some universal clock ticking the same for everyone. It's dynamic. It's elastic.
It's woven into space, right? Spacetime.
A space-time fabric. And it stretches and it squeezes. If you fly really fast in a spaceship, your clock ticks slower than mine back here on Earth. If you hang out near a black hole.
Your clock slows to a crawl. The twin paradox.
Precisely. So time is relative. It's a coordinate like left, right, or up, down. But it's a bendy one. It's part of the geometry of the universe.
Okay, so that's rule book 1. Time is a flexible personal dimension. What about rule book 2?
Rule book 2 is quantum mechanics. The laws for the very, very small. Atoms, electrons, photons, all the tiny particles that make up you and me and everything else.
And what does it say about time?
It says the exact opposite. In standard quantum mechanics, time is rigid. It's absolute.
How so?
It's what physicists call an external parameter. Think of it like a metronome sitting outside the experiment. It just ticks away, tick-tock, tick-tock, at a steady universal pace.
And it doesn't care what the particles are doing.
Not at all. It's a rigid background stage. The particles can dance and interact and do all their quantum weirdness, but the stage itself, the clock, is completely unaffected. It's just there.
So Einstein says time is a participant in the dance. Quantum mechanics says it's the unchanging stage the dance happens on.
You've nailed it. That is the fundamental conflict. And it works. It's fine as long as you keep them separate. You use Einstein for the cosmos. You use quantum mechanics for your phone's processor.
But the universe doesn't keep them separate. The Big Bang was both incredibly massive and incredibly small.
Exactly. The ultimate goal of physics, the Holy Grail, is to unite them. A single theory that explains everything. Quantum gravity.
And I'm guessing that when you try to write the equations for that, time becomes the big problem.
It becomes the problem. When you try to merge the math of these two frameworks, the equations, they break. and they break in a very specific and terrifying way.
This is where that Wheeler-DeWitt equation comes in, right? The source material really focused on this.
It's the classic example. Back in the 1960s, John Wheeler and Bryce DeWitt tried to write a single equation that describes the quantum state of the entire universe. They took Einstein's ideas about geometry and smashed them together with the rules of quantum mechanics.
And what happened?
When they worked through the math, when they simplified the equation, the variable for time, the letter T, it vanished.
It just disappeared. It completely canceled out. The final equation basically says that the rate of change of the universe is 0.
Wait. An equation to describe all of reality, and the result is nothing ever happens. That's it. It describes a static, frozen universe, a block. It contains every possible arrangement of everything all at once, but there's no flow from one moment to the next.
That's what they call the problem of time.
That is the crisis. Our best attempt at a fundamental equation says change is an illusion. But we look around, and my coffee is getting cold. Things are obviously changing.
So the math is just wrong then.
Right.
I mean, how can you trust an equation that says I'm not getting older?
And that is the terrifying part. We don't think the math is wrong. Individually, general relativity and quantum mechanics are the most precisely tested theories in the history of science. They work perfectly. It's only when they're combined that time goes away.
So either our perception of time is a profound illusion,
or we are missing something fundamental about how time is generated.
Which brings us to the, let's call it the classic explanation, the one I learned in school. The bandage that physics has used for a century to explain the flow of time.
Entropy, the arrow of time.
Right. The second law of thermodynamics. Can you just refresh us on that? The shattered glass idea.
Of course. The second law says that in an isolated system, disorder or entropy tends to increase over time.
Things get messier.
Things get messier. If you drop a pristine, ordered coffee mug, it shatters into a disordered pile of 100 pieces. You will never, ever see those 100 pieces spontaneously leap off the floor and reassemble themselves back into a perfect mug.
Because there's only one way to be a perfect mug, but a billion ways to be a pile of broken shards.
Precisely. The universe moves from unlikely ordered states to much more probable disordered states, and we just label that direction of increasing messiness as forward in time.
This has always felt pretty intuitive to me. My desk gets cluttered, not cleaner. So if entropy explains the arrow of time, why are we even having this conversation? Why is this new information idea even necessary?
Because entropy is more of a description of what happens, not a fundamental explanation for why time exists. And the source material points out two massive holes in the argument.
Okay, what's the first one?
The first is that the fundamental laws of physics themselves don't have a preferred direction in time. They are, as we say, time-symmetric.
Meaning they work just as well forwards as they do backwards.
Exactly. If you watch a video of two billiard balls colliding, you can't tell if I'm playing it forwards or in reverse. The physics is identical. Schrödinger's equation, Newton's laws, they don't care about past or future.
So, if the basic rules for the atoms don't have an arrow of time, how can the mug made of those atoms have one?
You can't build a one-way street out of two-way birds. It feels like you're smuggling the conclusion in somewhere.
Okay, that's a big hole. What's the second one?
The second one is even bigger. It's called the past hypothesis. For the whole entropy argument to work, for the universe to be getting messier now, it must have started in a state of absurdly, unbelievably low entropy.
The Big Bang had to be perfectly neat and tidy.
Incredibly tidy. And statistically, that's just bizarre. It's like walking down the beach and finding a billion grains of sand all lined up in a perfect row. You wouldn't think it just happened by chance.
You'd assume someone or something set it up that way.
Right. But the entropy theory just says, well, it started out tidy. It doesn't explain why. It relies on this 1 in a trillion initial condition as a given. It feels like a cheat.
So to sum up the problem, our deepest math says time doesn't exist, and our best explanation for it relies on a cosmic coincidence that we can't explain.
We need something deeper. And that's where this quiet revolution begins, the shift away from just thinking about matter and energy and towards thinking about information.
This is where things really took a turn for me in the reading. We need to be very clear about what we mean by information. Because normally I think of it as data, the words on a page. It's abstract.
It feels abstract. But the sources we're looking at treat information as a physical quantity, as real as a rock or a beam of light.
As real as mass.
Not just as real. In some sense, equivalent to mass and energy.
Okay, you got to explain that. I can put a rock on a scale. I can't weigh an idea.
Well, this goes back to the 1960s, to a physicist at IBM named Rolf Landauer. He established a fundamental rule called Landauer's principle, and it's what connects the abstract world of bits and bytes to the physical world of thermodynamics.
Is this related to that old thought experiment, Maxwell's demon?
It's the solution to Maxwell's demon, yes. The demon was this imaginary creature that could sort hot and cold molecules, seemingly violating the second law of thermodynamics by creating order from chaos.
Right. It could make one side of a box hot and the other cold for free.
Seemingly. But Landauer realized the demon has to know which molecules are which. It has to measure them. It has to store that information, even for a moment. And then, to keep sorting, it has to forget the previous measurement to make room for the next one.
So forgetting costs something.
Erasing information has a physical cost. That was Landauer's great insight. He proved that to irreversibly erase one bit of information, to reset a 1 to a 0, you must dissipate a tiny but non-zero amount of heat into the environment.
So deleting a file on my computer actually generates a tiny puff of heat.
A truly infinitesimal amount, but yes. Deletion is heat, and heat is a form of energy. And we know from Einstein's famous equation, E equals mc squared, that energy and mass are two sides of the same coin.
So, information is tied to energy, which is tied to mass.
It's physically tethered to the world. It's not a ghost in the machine. In a very real sense, it is part of the machine.
Let me see if I've got this. If I have two identical hard drives, and I fill one up with a complex movie and leave the other one blank, does the full one technically weigh more?
In principle, yes. The difference would be smaller than the weight of a single atom, but it is not zero. A drive full of complex, high-entropy data contains more energy than a formatted drive of all zeros.
Okay, that grounds it for me. It's real. And this reality of information is where the new theory of time comes from.
It's the key. Because once you accept that information is physical, you collide head-on with the biggest puzzle in modern physics, the black hole information paradox.
It always comes back to black holes, doesn't it?
They're the ultimate laboratory. They're where gravity and quantum mechanics are both pushed to their absolute limits.
So Stephen Hawking, he figured out that black holes aren't actually black. They leak.
They radiate. They glow with what we now call Hawking radiation, and over immense timescales, they can completely evaporate and disappear.
And this created a problem.
A universe-sized problem. Imagine you take a library of books, all that information, all those stories, and you dump it into a black hole. That information is now inside, but then, over trillions of years, the black hole evaporates into nothing but random thermal radiation.
Where did the information in the books go?
Exactly. If the black hole is gone and all that's left is random heat, the information seems to have been deleted from the universe.
And that's not allowed.
It's a cardinal sin in quantum mechanics. There's a strict law called unitarity, which says that information can never, ever be truly destroyed. You can scramble it, you can hide it, but you should always, in principle, be able to piece it back together. A black hole that deletes information breaks quantum mechanics.
So who won? Hawking or quantum mechanics?
In the end, almost everyone agrees that quantum mechanics has to win. The information must be preserved. It has to somehow be encoded in the radiation that leaks out.
And this whole fight forced physicists to take information seriously.
It forced them to see information not as something that describes reality, but as a fundamental ingredient of reality.
Yeah.
Maybe even more fundamental than space and time themselves.
Okay, so let's make the pivot. If information is the real bedrock, how do you build what we feel as time on top of that foundation?
This is the heart of the new model. The idea is to stop thinking of space-time as a smooth, empty stage.
An empty container.
Right. Instead, you have to start thinking of it as a storage medium, a physical substrate.
Like a cosmic hard drive.
That's one analogy. The source material uses the idea of a space-time lattice, or space-time cells. Imagine space isn't continuous. Imagine it's made of tiny, fundamental, discrete units, pixels of reality.
Okay, I'm with you.
And these cells aren't just empty placeholders. They have a job. Their job is to record.
Record what?
Interactions. Every time two particles collide, every time a photon of light bounces off an electron, that's an event. The theory proposes that these events leave a physical mark, a trace, an imprint on the structure of the space-time cells themselves.
So the fabric of the universe is keeping a logbook.
It is the logbook. This is the crucial shift. The universe doesn't exist in time. It generates time by writing its own history into its own structure.
I love that image. But what does it mean mechanically? How does writing a logbook create this feeling of a second passing and then another.
It comes down to irreversibility. Think about the difference between the past and the future in this model. The past is what has already been written down. The future is the blank part of the page.
Okay.
Now, the key assumption is that you can't erase the ink. Once an interaction happens, the information about it, the entanglement, the correlations, leaks out and gets imprinted on the environment on this space-time lattice.
You can't put the genie back in the bottle.
You can't globally unwrite an event, and because of that, the record can only grow.
The file size only gets bigger.
Precisely. The arrow of time, in this view, isn't about entropy or things getting messy. It's about the amount of information in the universe increasing. We experience time moving forward for one simple reason. There's more information in the universe now than there was a nanosecond ago.
So the present moment is just the leading edge of the recording head, laying down a new track.
That's a perfect way to put it. And this completely reframes our place in the cosmos. We aren't just passengers on a river of time that was already flowing.
We're making the river flow.
Our actions, our existence, every single interaction between particles is what carves the channel. We are actively constructing space-time by living in it.
You just said something that I want to pause on. Constructing space-time. Does this recording process actually change the physical geometry of space?
According to the theory, yes. And this is where it gets really exciting because it might just solve one of the biggest mysteries in astronomy.
Dark matter.
Dark matter.
Okay, let's set the scene for this because it's a huge claim. The standard story of dark matter is that our galaxies are spinning too fast.
Right. It's a simple observation. You look at a spiral galaxy, you measure the speed of the stars, you expect the stars on the outer edge to be moving much slower than the ones near the center because gravity gets weaker with distance.
Just like in our solar system, Pluto moves way slower than Mercury.
But that is not what we see. When we look at galaxies, the rotation curve is flat. The stars on the very edge are whipping around almost as fast as the stars in the middle.
They're going so fast they should just fly off into space.
They should be flung out. The gravity from all the stars and gas we can see isn't nearly strong enough to hold them in orbit. So for decades, astronomers have assumed there must be some extra invisible stuff providing the extra gravitational glue.
An invisible halo of dark matter.
A mysterious particle that doesn't interact with light, that we can't see, but that has a lot of gravity. And we've spent half a century and billions of dollars building incredibly sensitive detectors deep underground trying to catch one of these particles.
And the result has been nothing.
A complete blank. Not a single confirmed detection.
So how does this time as memory idea solve the problem without inventing a new particle?
It offers a truly radical alternative. It says you don't need invisible matter. The extra gravity isn't coming from stuff, it's coming from the space-time fabric itself.
How?
Remember Landauer's principle? Information has an energy equivalent. And energy curves space-time. That's just general relativity.
Okay.
So if space-time is recording the history of interactions, then a region of space that has a lot of history, like a galaxy, which has been around for billions of years with stars forming and exploding and gas clouds colliding, is saturated with these records. It's heavy with information.
The memory of the galaxy gives it extra mass.
It creates an effective gravitational pull. The space-time in and around a galaxy is different from the space-time and the empty void between galaxies. It's been altered by its own past.
So the stars on the edge are orbiting so fast, not because of an invisible cloud of particles, but because they're moving through a space-time that is dense with the memory of everything that happened before.
That's the proposal. It's not ghost matter holding the galaxy together, it's the galaxy's own history.
That is profoundly elegant. It ties the quantum world of information directly to the cosmic scale of galaxies.
It suggests that the arrow of time and the mystery of dark matter might not be two separate problems. They could be two symptoms of the exact same underlying process. The universe accumulating a record of its own existence.
I have to be the skeptic here, though. It's a beautiful story. It ties up loose ends. But is it science? Or is it just a nice philosophy? Can you test it?
That's the most important question. And the answer is yes. Unlike a lot of other ideas in quantum gravity, this one makes concrete, falsifiable predictions.
Okay. How do you test if the universe is a hard drive?
One place to look is, again, black holes. In the standard picture, the Hawking radiation they emit is purely thermal. It's random. It's basically just heat, like the glow from a hot piece of coal.
Just noise.
Exactly. But if this information theory is correct, and the information of things that fell in must be preserved, then that radiation can't be perfectly random.
There has to be a signal hidden in the noise.
There should be subtle correlations, patterns, a kind of structure hidden in the radiation that encodes the history of the black hole.
Can we see that?
Not yet. We'd need telescopes with far greater sensitivity than anything we have today. But it's a clear prediction. The theory says Hawking radiation has structure. The old theory says it doesn't. One day we'll be able to look and see who's right.
So that's a test for the future. Is there anything we can do now?
There is. We can test it in the lab.
On a tabletop?
On a microchip, using quantum computers.
Ah, of course.
Researchers can use qubits, the quantum equivalent of computer bits, to build tiny simulated universes. They can program a handful of these qubits to interact according to quantum rules.
They create spacetime cells on a chip.
Essentially, yes. And they can set up these systems to be perfectly reversible. In theory, you should be able to run the whole process backwards without any issue. There should be no inherent arrow of time.
But what do they find?
They find that as soon as the qubits interact, the information about that interaction starts to spread out through the system. And this process of information spreading out, of becoming correlated with the wider environment, creates an effective arrow of time.
Even though the underlying laws are reversible?
Yes. They can literally watch informational time emerge from the system's own processing. It shows, on a small scale, that you don't need a master clock to have time. You just need a system that records and spreads information.
That's incredible. It's like building a little toy universe that learns to have a past and a future all by itself.
It's powerful evidence for the core mechanism of the theory.
This whole thing is such a monumental shift in perspective. We tend to think of the laws of physics as being imposed on the universe from the outside, like a cosmic rule book that was written before the game started.
The Platonic view of laws, yes.
But this theory suggests the rules, or at least some of them, like time and gravity, are actually emerging from the game as it's being played.
That's a great way to describe it. It's the difference between a scripted play and an improv show. In the old block universe view, the script is already written. Past, present, future, all there. We just read our lines.
In this view, there is no script.
There is no script. We are writing it line by line with every interaction. And once a line is spoken, it's part of the permanent record. It's canon.
Which leads me to something that's been bothering me. If the universe remembers everything, if every single thing that happens is etched into the geometry of space, does anything ever truly get lost?
That's the deepest philosophical implication of this entire framework. In a universe where time is the accumulation of information, the concept of gone doesn't really mean anything.
We think of the past as being gone. It's over. It exists in my memory, sure, but it's not physically here anymore.
But if this theory is correct, that's wrong. The past is physically present. It's encoded in the current structure of the universe. The configuration of everything right now is the complete record of its history.
So, our lives aren't just a fleeting sequence of events. They're a permanent contribution to the structure of reality.
You're not just passing through the universe, you are actively building it. Every choice you make, every word you say, every breath you take is adding a new, permanent piece of information to the cosmos. You are, quite literally, making the universe heavier with meaning.
Let me bring it back to the beginning for a moment. The frozen universe from the Wheeler-DeWitt equation. Does this new theory solve that? Does it explain why we perceive flow if the fundamental equation is static?
It does. It reconciles the two views. From a God's eye perspective, outside of everything, the universe might well be a single, static, four-dimensional block of information. Timeless.
The frozen block still exists.
But inside that block, for any observer living within it, the information is not distributed evenly. There's a gradient. The structure itself contains a sequence. It flows from states of less information, the beginning, to states of more information.
So the block is static, but the pattern written on the block creates the appearance of a movie playing.
Exactly. Time is the gradient of information, just like a hill is a gradient of elevation. The flow of time is just us experiencing that change from less complexity to more complexity.
It really is a thermodynamics of time, then.
That's the term for it. In the same way that temperature isn't a fundamental property of a single atom, it's an average property of many atoms. Time isn't a fundamental property of the universe at the smallest scale. It's an emergent statistical property of information.
So if I could zoom in all the way down to those space-time cells, I wouldn't see a tiny clock ticking.
No. You would just see a network of connections, a web of information. Time is the shadow cast by the processing happening on that web.
What does this do to ideas like time travel? Because if time is just another dimension, sci-fi loves to talk about flying backwards along it.
Well, it makes time travel to the past profoundly difficult, if not logically impossible.
So, no going back to fix my mistakes.
Think about it. If time is just a road, maybe you can turn your car around. But if time is the irreversible accumulation of a cosmic record, you can't go back.
Why not?
To go back to yesterday, you would have to find a way to erase today's information from every single particle in the universe that it has touched. You'd have to undo every single quantum record that has been made.
You would be fighting against the fundamental tendency of the universe to record things.
You'd be fighting unitarity. You'd be fighting the second law of thermodynamics on a cosmic scale. The past is locked because it's already been written. The future is open because the page is still blank.
That, at least, feels right. It secures the past. You can't go back and create a paradox by, killing your own grandfather.
Because the information that your grandfather lived is already a structural component of the universe you inhabit. It's part of the geometry you're standing on.
So we lose the DeLorean, but we get a universe that remembers us and an explanation for dark matter without needing magic particles.
I'd call that a pretty good trade. It's a much more elegant picture of the cosmos.
Let's try to sum this all up. It's been a lot to process.
It has. Okay, the big picture. 1. Our two best theories of physics, relativity, and quantum mechanics clash over the nature of time, leading to the problem of time, where it vanishes from the math.
2. The old solution, entropy, explains the arrow of time as increasing disorder, but it has to assume the universe started in a bizarrely tidy state for no reason.
3. The new solution proposes that information is physical and that space-time itself is a memory system that records every interaction that ever happens.
4. Time is the process of that record growing. The flow we feel is just the universe's memory getting larger and more complex.
And 5. This process of information accumulation actually has a gravitational effect, which might explain the mystery of dark matter without needing any new particles.
And the big takeaway for us? Living in it.
We need to move from thinking about the universe as a passive stage for events to seeing it as an active system that is constantly learning and remembering. It's a participant in its own story.
When we started, we talked about that gut feeling of time. And usually when physics comes along and explains something, it could feel like it's taking the magic away. A rainbow is just light refraction. Love is just chemicals.
It often feels reductive, yes.
But this
Yes.
doesn't feel reductive to me. Time is memory. It feels significant. It feels like it gives a cosmic weight to our experience. It validates that feeling that the past isn't just gone, that it matters.
It's built into the very foundation of the present. I agree. It gives a literal weight to history.
So before we wrap up, I want to leave you with one last question to think about.
Let's hear it.
Okay, so the universe is a recording device. It's a library at everything that has ever happened, written into the geometry of space. My question is, who's reading it?
That is the question, isn't it?
Is the writing of the book the whole point? Or is there a reader? And if the record can never be fully erased, if every moment is permanently stored, does that mean, in a very real physical sense, that nothing ever truly ends? That we're all just permanent features like mountains or rivers on the landscape of spacetime?
If the theory holds, the answer would have to be yes. Your existence is a permanent scar on the geometry of reality.
Wow. I think I'm going to walk a little more deliberately today. I'm literally carving my path into the universe.
Make it a good one.